Welcome to Unique Academy YouTube channel. So in this video, we will see gate problems from thermodynamics. So question number 1. So the refrigerator working on a reversed Carnot cycle. So reversed Carnot cycle, so if you take this higher temperature, refrigerator, lower temperature. Okay. So the work is given into the system, work input. So Q1 is supplied, Q2. COP of refrigerator. So refrigerator working on a reversed Carnot cycle. So this is reversed Carnot cycle. So that means COP of refrigerator, which is Carnot refrigerator, is lower temperature by this temperature difference. So if it works as a heat pump, so COP of heat pump, Carnot heat pump is equal to same temperature limit, right? So if it works as a heat pump, then it is the same temperature limit. So this will be 1 plus COP of refrigerator Carnot. Okay, so we know that COP of heat pump 1 plus COP of refrigerator. COP of refrigerator is given as 4. COP of refrigerator, Carnot refrigerator is given as 4. So that means 1 plus 4 equal to 5. And the work input to the heat pump. So COP of the heat pump you can write as desired effect is Q1. So this is the heating effect for Carnot heat pump. Heating effect is Q1 by work input. So what is asked is the heating effect. So this is the heating effect. This is the cooling effect. Maybe this you can write as Q2 by, this is for the refrigerator, cooling effect. So your heating effect Q1 is equal to 5 into the work input. Work input is 1 kilowatt. So this will be 5 kilowatt. The heating effect will be 5 kilowatt. So the answer is C is the answer. So a real gas passing through an insulated throttling valve. So you have a throttling valve. So in the throttling, enthalpy remains constant. H1 will be equal to H2. but the temperature may increase or decrease or the same. Depends on the Joule-Thomson coefficient. So we have seen if the Joule-Thomson coefficient Uj is positive, cooling effect. Joule-Thomson coefficient is negative, heating effect. So Joule-Thomson coefficient is 0, temperature constant. So if you see that, so what is this Joule-Thomson coefficient? It is dT by dP at enthalpy constant line. So if you take temperature versus pressure, if you try a constant enthalpy line, it goes something like that. So there will be a curve. So this is the inversion curve. This is constant enthalpy line. So you will find that the slope will be positive here. Slope is positive here. Slope will be negative here. So in the slope negative, if you, so in the, your pressure will be dropping. So there is a pressure drop. So this is the direction. There is a pressure drop. So when the pressure is dropping in the throttling process, temperature increases in the negative side of Joule-Thomson coefficient. So here you have cooling effect. Here you have heating effect. So a real gas passing through an insulated throttling valve, the outlet temperature of the gas may be higher, lower, or same with respect to inlet temperature. That is what is based on the Joule-Thomson coefficient. So this will be your answer. So we go to the next question. So the saturation pressure of the liquid is represented by the equation. So you are given an equation. A and B are constant. T is the absolute temperature. For this substance, which of the following expression for specific entropy difference between the saturated vapor and saturated liquid phase is correct? Now you see, so if you look at the Clausius-Glebran equation, Glebran equation, maybe spelling you can check. So this will be your dP by dt. Saturated condition will be equal to HFG by temperature into VFG. So we have written this HFG. You see, we know that TDS equal to DH minus VDP. So this Clausius-Glebran equation is applicable to a phase change process. So this is applicable to the phase change process. In the phase change process, pressure and temperature is constant. So this will be 0, dP will be 0. So ds will be equal to dh by t. And temperature also constant. So this you can write as Sg minus Sf is equal to Hg minus Hf by T. Temperature is constant. So this will be your Sfg equal to Hfg by T. So Hfg by T, you can write Sfg. So from here, we can understand from here, Hfg by T is equal to Vfg dP by dt saturated. So this will be your Sfg. Now we need dP by dt at saturated. That you can get from here. So this equation, if you differentiate 1 by P saturated into dP by dt, because this is in the saturated condition, is equal to A is constant, so 0. So 0 minus B into 1 by T. So this will be minus 1 by T squared. If you differentiate with respect to T. So from here you can understand that dP by dt at saturated is equal to this minus minus plus B saturated by T squared. So that you can substitute here. So this will be B by T squared. So the answer is matching for B. This is the answer. So now a refrigeration cycle, the ratio of actual COP to the COP of a reversible refrigerator operating between the same temperature limit is 0.8. So that is COP of refrigerator actual by COP of refrigerator reversible refrigerator, that is Carnot, equal to 0.8. So here the temperature limits are given. So higher temperature will be 51 degree. So it supplies Q1. So refrigeration. So you have to give the work input Q2. Lower temperature T2 given by minus 30 degrees centigrade. Okay, so you got this. The cooling capacity of the plant is 2.4 kilowatt. Cooling capacity means Q2. Q2 is the cooling capacity, 2.4 kilowatt. Then the power input to the refrigerator. So now the COP of refrigerator actual is cooling capacity by work input. Cooling capacity is there. So what is asked is the power input. So work input is equal to Q2 by COP of refrigerator actual. So this you can find getting the Carnot COP of refrigerator. COP of refrigerator Carnot is equal to T2 by T1 minus T2. So you substitute in Kelvin T2. To 43 Kelvin. So this will be in 243 Kelvin. This will be 324. Substitute that 243 by 324 minus 43. Three. Three is the COP of Carnot refrigerator. So COP of actual refrigerator. 0.8 into 3, 2.4. So once you know the COP of the actual refrigerator, then you can get to the power input. Q2 is 2.4 kilowatt by 2.4. 1. So power input is 1 kilowatt. So answer will be A. A is the answer for question number 4. So if you see there are 4 different entropy temperature diagram representing a liquid to vapor phase transition process of a pure substance in a closed system undergoing a constant pressure process. So which of the diagram which represents the, so now if you look at our TS diagram, so if you see our TS diagram, so we know TS diagram very well. So the constant constant pressure process will be like this. This is the pressure constant line. Now what is asked is the entropy is in the y coordinate, same thing. So during a phase change process, the liquid to vapor phase. So this is liquid plus vapor. This is the vapor. This is the liquid. So liquid to vapor phase change. But we wanted it in a entropy temperature diagram. So what way it will happen? So this dome will come something like this. This is the way it will be. Nearest to the temperature liquid side, liquid plus vapor, vapor side. So this is the critical point. So this is your critical point. Now constant pressure line. So it goes something this way. This is the line. Pressure constant line. So this, if you look at that, it matches with this. None of the other things matches. Maybe the first A is the answer. This will be your answer. Thank you for watching this video. So if you are happy with this video, please subscribe this channel and share this video to your friends who are preparing for GATE mechanical engineering subject. If you want to join for GATE 2026 video course, please contact the number given here. And you can also go to the website for the admission details. Thank you.